Good morning. If you can hear me, just raise your hand or put a chat in the chat window. Just say yes, because from the experience of last time, I have muted all your volumes for in the beginning. Yes, Ruturaj. Yes. I can see Vaibhav.
Yes, sir.
There is no mercy. Who is no mercy?
Rashish.
Rahul. Yes. Kedar. Shivanjali. Jyoti. Vaishnavi. Prathamesh. Samruddhi. Prathamesh Kolekar, I guess. Then Prathamesh Kulkarni. Okay, so I can see around 15 of you. Yeah. Shall we start? Is everybody able to hear me?
Yes.
Yeah. Okay. So, good morning again. Hope the last lecture you have enjoyed, and after that you have studied a bit about that, right? Okay. So today what we are going to cover is the portions from the fourth unit. I have already circulated the presentations from that. Hope you have gone through that. Okay. Some of the part of what I have circulated was already covered in the classes, right? About the frequency domain specification, basic things. What we will see today is the polar plots. Okay. Okay. So can you see this presentation now? Polar plots. Yes.
Yes.
Yeah.
Yes, sir.
Yeah. So we will continue with it now. This is part of the fourth unit. Polar plot is one of the techniques in the frequency domain analysis. You have already seen one, which is Bode plots, right? We have covered Bode plots, which is also a frequency domain technique. And today we will see polar plots and Nyquist stability criterion. If you can recall, the Bode plot is a frequency domain technique, but when you do the analysis and you plot the Bode plot, what you need is a semi-log paper, and you create two graphs, right? One is the magnitude plot and another one is the phase plot, right? So instead of two plots, what we can do in polar plots is it is also a plot of a sinusoidal transfer function g of j omega, and it is a plot of magnitude versus the phase angle. Okay, in Bode plot what we have seen, there are two separate plots, magnitude versus frequency and phase versus frequency. But in polar plots what we have is magnitude versus the phase angle. Okay, so what we are actually doing is in polar plot, what we actually do is it is the locus of vectors g of j omega, angle g of j omega, and omega is varied from 0 to infinity. Okay. Uh, right. So if you can see this graph here, we start with omega equal to 0 and it is varied from 0 to infinity, and this is one of the sample graphs. So in this case, for example, it starts omega equal to 0 here, and as we increase omega at a particular location, when omega equal to infinity, it is the magnitude becomes 0. This is one of the sample polar plots. Okay, so what you can see in this graph is there is a single graph where magnitude and phase can also be seen, right? So each point on this polar plot of g of j omega represents the terminal point of a vector at a particular value of omega. Like this vector, if you can see, this is a vector. The length of this vector is what? It is the magnitude of this g of j omega, and this angle, the uh, angle of this vector is the phase angle of the function of g of j omega, right? If you project the this point, if you project the terminal of the vector onto the two axes, then what you get? You get the real and imaginary part of the magnitude, a real and imaginary part of the of g of j omega, right? So as I said, the advantage of using polar plot is it depicts the frequency response characteristics of the system or the entire frequency range in a single plot. What you are getting? We are getting only a single plot on which we get full frequency response characteristics. However, the disadvantage is we cannot clearly indicate contribution of each individual factor. Now, what does it mean? If you recall, in the Bode plots, what we have done, we used to have some sections for each component, like integral or derivative component, or a first order factor in numerator denominator. For each of those components, we used to have separate contribution, and that was clearly visible on the Bode plot. However, on polar plots, there is no such possibility of finding out contribution of each factor. Okay. Anyway, but of course, there are certain advantages and disadvantages of everything. So the advantage we'll look at now, that polar plot depicts the frequency response characteristics of a system or the entire frequency range in the single plot. That is the advantage. As usual, the positive phase angle is measured counterclockwise from positive real axis. So this is nothing new. The negative phase angle is measured clockwise from positive real axis. If you want to measure like this, when you go from positive real axis anti-clockwise, then the angle is positive. If you go clockwise, then the angle is negative. Okay. One important thing to note is we are not really interested in the exact shape or exact points of all the polar plot. Okay. What is more important is the starting and ending points, which means omega equal to 0 and omega equal to infinity. These are the starting and ending points of the polar plot. These are very important. So most of the times while we are calculating the polar plots, what we do, we calculate the values of magnitude and phase at the terminal points. The terminal points are omega equal to 0 and omega equal to infinity. Okay. If you have any doubts, you can ask anytime, right? Okay. Okay, so let's, like we did in the at the time of Bode plots, how would a polar plot of an integral factor look like? Let's see. So the polar plot of an integral factor means 1 upon s, means in a frequency domain, say g of j omega is equal to 1 upon j omega, is the negative imaginary axis. Now, how can I say this? See, P of j omega is equal to 1 upon j omega. This is the integral factor. So, if we multiply and divide by minus j omega, what we get? We get minus j 1 upon omega, right? So, for this in polar forms, the magnitude of this is 1 upon omega and the phase angle is minus 90, right? Okay, so how can you plot this? Like this is the imaginary axis and this is the real axis. So what we say, minus 90 degree is the angle, and at omega equal to 0, what is the value of magnitude? It is infinity, right? At omega equal to infinity, what is the value of what is the magnitude of g of j omega? It is 0. So the plot of this g of j omega for g of j omega is equal to 1 upon omega is the negative real axis. Negative imaginary axis, right? Okay. If we have a derivative factor, means g of j omega is equal to j omega, then obviously it will be a positive real axis, because in polar form, g of j omega is equal to omega angle 90 degree. Means what? 90 degree angle at omega equal to 0, value of magnitude of g omega will be 0. At omega equal to infinity, magnitude will be infinity. So it is the positive imaginary axis. Right? So these two are very simple. Now if we have a first order factor in numerator, like g of j omega is equal to 1 plus j omega. Now what will be the shape of the polar plot for this case? Can somebody guess? Yes? Can you listen? Is everybody able to listen me?
Yes.
Yes? Yeah. So can you guess some, can anyone guess what will be the shape of this factor? Like what we have done? We just substitute omega equal to 0 and omega equal to infinity in this equation and find out the magnitude and phase. So if I substitute omega equal to 0, real part is 1, imaginary part is 0, right? Similarly, if we go from 0 to infinity, what we get? Real part always remains 1,
Well,
right? Real part always remains 1. What only changes
yeah.
the imaginary part? Means it will be like this. It will be a line parallel to the imaginary axis, parallel to the positive imaginary axis, let's say. Okay. When the factor, order factor is in the numerator. Okay. This is clear up to this point.
Yes.
Now comes the tricky part. If the polar plot, if the function has a first order factor in denominator, now what will happen? First, we will have to little bit simplify the function, okay? Because what we want it in form of a real and imaginary part, so that we can find out the magnitude and phase, right? From this function directly, we cannot find out the phase and magnitude. So first we'll have to convert it in some real and imaginary section like this. Okay. Are you getting what we have done here? We have just multiplied the numerator and denominator by 1 minus j omega. What is this? It is the complement of this, complex conjugate of this, right? 1 plus j omega was in the denominator. So we just multiplied by 1 minus j omega. So what we get? Multiplication of these two, 1 plus omega square, right? J omega into j omega is minus omega square, and this minus sign, so we get omega square, 1 plus omega square. In the numerator, what remains is 1 minus j omega. So when we split these two, we get the real part as 1 plus omega square, and we get imaginary part as, this is the real part what we get here, and the imaginary part is this. So from these two, what can we do? We can find out the magnitude and uh, or simply the real and imaginary parts, right? From when we substitute omega equal to 0, what we get? Real part omega equal to 0, so real
0.
part is 1 upon 1 plus 0 is 1. And when we substitute omega equal to 0, here imaginary part is 0, right? Similarly, if we calculate for some values, what we get for 0.5 of the values, and the last value what we are interested in is infinity. When we substitute omega equal to infinity, what we get? This is 0 and this is also
0, 0.
0, right? So now how to plot this? This is the table we have got, right? This table, this whole table I have just taken in the again here, okay? Now, for omega equal to 0, real part is 1. So I have plotted it here. For omega equal to 0.5, real part is 0.8, imaginary part is minus 0.5. So like this, if I plot the values, what we get? It is a curve like this. It is almost a semicircle, almost. Okay. This is what we get for the first order factor in denominator. Okay. Now, if we try to find out, see what we have plotted here is only based on the real and imaginary part, right? But it will not always be possible for us to calculate real and imaginary parts for all the values. Okay. So we are coming to some other way of plotting. Okay. So for these real and imaginary values, we have calculated magnitude and phase angles. Okay. So magnitude of for the g of j omega for omega equal to 0 is obviously 1. So it is a vector of length 1 for omega equal to 0, right? And angle of that vector is 0 degree, means the positive real axis. Now similarly, all these calculations if you can do, you can find out that these are the magnitude and phases of each of them. We get the same curve. Obviously the curve will not be different, but what I'm trying to do is we want the magnitudes and phase of the terminal points. Okay, this is very important to note. Okay, magnitude 1 angle 0 and magnitude 0 angle minus 90. Okay, so these are the things that we must take into consideration. Okay, so when we plot it, we have to take it the angle here. You can see it goes into here in this way. Okay, so the plot is like this, and then it goes back to here. Okay, this is what this is the polar plot of the first order factor in denominator. So what it actually is, it is like a simple RC filter. If you remember, the transfer function of a simple RC filter is 1 upon 1 plus ST, right? T being the time constant of the system. In this case, the T was, what was in this case? T was equal to 1, right? So if we want to generalize for a simple RC filter, this is a generic equation 1 upon 1 plus j omega t. So you can see the plot is the same, right? Plot is same. At angle 45, the length was 1 by root 2. Was it correct? At angle 45, it was 0.71 by root 2, right? We are getting the same things. Okay, it is not different. So this is what is the generalized form of the polar plot. Okay, now if we add uh, what we have added here, we have added a integrator. We have added an integrator in the system Like here is a first order factor in the denominator and integrator is added. So what we did in the previous case, we are doing the same similar kind of thing and simplifying the equation, and what we get, the real and imaginary part of the two things, right? The real part and imaginary part of this equation. So as I said, we are not really interested in every value of the curve. What we are more interested in is the values at the terminal points, omega equal to 0 and omega equal to infinity. So if you substitute omega equal to 0 here, what we get? Minus t minus j omega. And the value is, magnitude is infinity and angle is minus 90. At omega equal to infinity, what we get? Magnitude at 0 and angle as minus 180. Okay. So this is how we have plotted that. If you can see at omega equal to 0, it means in this direction here. Okay. We start from omega equal to 0 and omega is increasing in this direction. You can see the arrow here. So at omega equal to 0, the magnitude will be infinity, right? And the angle, if you can see, this is minus 90 degree, right? This angle is minus 90 degree. And at omega equal to infinity, magnitude is 0. So if you can see here, the magnitude has reached 0 at omega equal to infinity. You see, this is the axis. Omega equal to infinity, magnitude is 0, and angle, you can see this is the negative real axis, right? Negative real axis is means minus 190. This is minus 180.
Hmm.
Right? You getting the point? So at omega equal to 0, magnitude is infinity and angle is minus 90 here, like this. And as we increase omega, we get angle as minus 180 and magnitude as 0, right? So the shape of the curve generally is asymptotic. You can see here what we said, it is infinity, magnitude is infinity and angle is 90. So where to draw this infinity? It is asymptotic to a line. This is the vertical line passing through minus t here. Okay, this will be minus t 0. That from that point it will be passing. This is the vertical line from through which the line will pass. Okay. Now similarly, we can draw certain plots, generalized plots for some complicated transfer functions when there are two first order factors. What we mean? Two poles. So in this case, the angles we can calculate in a similar way, and the shape will be like this. Now what has happened here? The angle here in this case is what? Minus 180, and here it is minus 90. So these things, this way we have to, now I will leave this as a part of your homework to how you can find out the real and imaginary part of this. Okay. Similarly, when things get added, the angles get added. Okay, the angles get increasing. In general, for one factor, the angle is 90. Angle contribution is minus 90. Like if you remember in the Bode plot also, each denominator factor was adding an angle of 90 degree, right? So similarly here also, it will keep on adding an angle of minus 90 degree. The point is, why we are all doing this? I mean, polar plot, why is it important to draw a polar plot, and what we are going to get from that? Ultimately, we are going to do system analysis, and what we want to find out whether the system is stable or not. What is the relative stability of the system? And for that, we will see how to find out how to go for the stability analysis. But before that, just take a look at an example uh, to draw a polar plot of the following open loop transfer function. Remember, once again, that we are always having an open loop transfer function, which we are using for polar plot, Nyquist plot, Bode plot, and all. We are not having the closed loop transfer function. Okay, open loop transfer function means either you can say GS or GSHS. In general, most of the times, HS is one in these cases. Okay, so polar plot for this open loop transfer function is given. So what can we do? Obviously, we substitute j equal to s equal to j omega to convert the transfer function into frequency domain. Then this is just multiplication, and again, like we have done in the previous cases, right? We have done in the previous cases, multiply and divide by the complex conjugate of this denominator, so that we get a real and imaginary part representation of the transfer function. This is the real part and this is the imaginary part, right? Now, just simplification. Again, we calculated some values for omega varying from 0 to infinity. Now, why we have taken these values? Just to get an idea of the shape, okay? And we plotted it like this. So if you just recall, before a couple of slides, we have seen when there are two factors. Here, what are the two factors? One is a first order factor and another one is the integrator. So when it is like this, the polar plot is in this way: omega equal to 0, value of magnitude is infinity, and it is going through this. It is asymptotic to this line -1 line going through this. And as we increase omega, at omega equal to infinity, the value of the magnitude is 0, right? Value of magnitude is 0, because real and imaginary both parts are 0. Okay, so this is what we have. This is how we calculate, okay, the polar plot. Now, as far as the stability of this polar plot is concerned, okay, as far as the stability of polar plot is concerned, we must remember what we have seen at the time of studying the Bode plot. For in the frequency domain, what we say, the system is stable when the gain margin and phase margin both are positive, right? You remember this? Both gain margin and phase margin are positive, right? When both these are positive, system is stable. And what is gain margin? Gain margin is the uh, reciprocal of the gain, reciprocal of the magnitude as at phase is equal to -180. You remember these things? The definitions of the gain margin and phase margin we have seen in the beginning, right? At the time of Bode plots, we have seen this. So if you look at the graph here, if you look at this graph, a sample sample um, polar plot we have drawn here. This shape is like this, okay? Okay, so if you see, this is the shape of the polar plot, okay? Now, if you look at the point A, if you look at this point A, what is the value of phase angle at this point? It is -180, right? The phase angle in this case is -180. You can see angle is -180. Okay, so at -180 degree phase angle, what is the magnitude? The magnitude is x. How do we calculate x? How we calculate the magnitude? It is the value of this vector, right? If you draw a vector, this is the vector that we have drawn, and the length of that vector is the magnitude, right? we saw in the very beginning in the diagram, right? So this vector, the length of the vector is x, that is the magnitude of the magnitude of g of j omega when the phase angle is minus 180. So this point actually is the omega pc, means phase crossover frequency, when the phase crosses minus 180. Okay. So at this point the magnitude is x, and therefore gain margin is 1 upon x. This formula we have seen at the time of studying Bode plot. Okay. Now what we say, gain margin should be positive. That is what the condition is for stability. So this translates into the system is stable if x is less than 1. Okay, if x is less than 1, why less than 1 means this? One means if you draw this unit circle on this and if the polar plot is going through inside the unit circle, if it is crossing the imaginary axis inside the unit circle, then the table. If this crossing point in suppose it is something like this, and this is the minus 1 point, okay, then the system will be unstable. Okay, so this is how we will find out the stability using the polar plots. Okay, have any questions in this part?
Sir, how to draw this circle?
Yeah, as I said, you don't really need to draw the full circle. Okay, most of the times what you need is like see, uh, what you are more what is more expected from you is uh, you have to know the terminal points, like this will be a first starting point, this will be the ending point, and you should know the um, basic shape of the for the factor. Like when you have a uh, first order factor in the denominator only, then the shape is like this. So this shape is not very important. Okay, you can have an have a not so correct shape also is okay. Okay, additionally what you can see is you may have one specific angle like 45 degree. For that you have a specific value, like I said, 1 by root 2. Also I have said 1 by root 2 for 45 degree. Now in this case you can see in this diagram there are not many values. Okay, only the starting point, ending point, and a center point. So just you can have very few number of values you can draw the shape. If you don't have the central value also may be sufficient, but what is more important is you must have the starting value, the ending value, and their angles. Okay, the angles are important. Okay, if you go through the notes also, I have added some more examples in that. Okay, uh, you can go to the notes in our uh, notes are uploaded on Moodle already. So you can see there how what happens to the angle and how to when the angle changes, you will have to do. Okay. So also take a look at those notes for this specifically for these angles and how to draw those angles. Okay. Yeah. Anything else? Hello.
Hello, sir.
No, sir.
Yeah.
Hello.
Yeah. Uh, if this section is clear, then I would like to move on to the uh, second section of this lecture, which is the Nyquist stability criterion, and Okay, so here we have the second very important topic, which is Nyquist stability criterion. Okay, uh, just to remember some of the basic things. Okay, because if you forget about or if you neglect those basic things, then it will be very difficult for you to understand what we are talking about. Okay, so whenever we talk about stability, when we say the system is stable, most important thing is the closed loop poles, right? The closed loop poles are the closed loop poles of the system are on the left hand side of the S plane, right? This is the most basic requirement of a system to be stable. Now when we say closed loop poles, those are actually the roots of the characteristic equation. Okay, this we have been talking about since a long time, like from the second or third unit, right? That all the poles or closed loop poles of the system must be on the left hand side of the uh, on the left hand side of the uh, all the poles should be on the left hand side of the system of the complex plane. Okay, now when we talk about this Nyquist stability criterion, okay, it is also determining the stability of the closed loop system from its open loop response and open loop poles. Okay, if you recall, just before a while I said that in Nyquist, in Polar, in Bode, all we are talking about is the open loop transfer function only. We don't see the closed loop transfer function. Okay, from open loop transfer function we find out the closed loop stability. Okay, so similarly in Nyquist stability criterion also we find out the closed loop system stability from its open loop response and open loop poles. Okay, now uh, as it is written in the first point, that roots of the characteristic equation. So what is the characteristic equation? It is 1 plus GSHS, correct? 1 plus GSHS equal to 0 is the characteristic equation, right? So what Nyquist criteria does is it relates the frequency response of G of j omega h of j omega. It means what? Open loop frequency response to the number of poles and zeros of 1 plus GSHS. Means uh, here I'm explaining the second point. The frequency response of G of j omega h of j omega is related with the poles and zeros of 1 plus GSHS that lie right half of the S plane. Means how many of those lie in the right half of S plane, and from that we can find out the stability. Okay. Now before we actually talk about what Nyquist criteria is doing, we have to understand one very critical thing, I would say, which is called mapping of one function, mapping of one section to another to a function. Okay, now let's take a look at a polynomial Q of S, which is the ratio of again two polynomials. Okay, these two polynomials are expressed as factors. Okay, S minus alpha 1, S minus alpha 2, S minus alpha m. So m factors in the numerator, n factors in the denominator are here in the polynomial Q of S. Okay, so this S, this variable S is a complex variable, sigma plus j omega. Therefore, the function Q of S is also a complex variable. Let's denote it as U plus JB. Okay, so what happens actually when we have this Q of S is for every point S in this S plane, this is the S plane. Okay, for every point S in this S plane at which Q of S is analytic, means Q of S has a single value for any value of S. there exists a corresponding point in the QS plane. Means for any point here, let's say this is S, there will be some point somewhere in the QS plane also. There will be a one-to-one relationship between the two planes. Okay. So when this function Q of S is applied on a variable S, whole of this S plane is converted into a Q of S plane. Okay. So the axis get converted from sigma plus j omega into u plus j omega. Okay. So if we traverse through a closed loop, through a closed contour, this is a contour, right? A closed contour, and you can see this traversing is how much? It is 2 pi. Since this is a closed contour, the angle traversed by this contour is 2 pi, right? It is taking a full turn, 360-degree. So QS also will have a full turn, a full 2 pi. Okay. This is one important thing to understand before understanding the Nyquist criteria. If this contour takes an inverse or anti-clockwise direction, okay, then there will also be a contour in the QS plane which will take a anti-clockwise direction, and again the traversing will be 2 pi or minus 2 pi. Okay, clockwise minus 2 pi, anti-clockwise 2 pi. Okay, so what is important to know is, if a contour is taking a full closed loop path in the S plane, it will also take a full closed loop path in the QS plane. Okay, this is the mapping plane. Okay, we are going to map the S plane into some another plane. Okay, now coming back to our Nyquist stability criterion, you have seen this representation GSHS many times. Do you remember this? GSHS is equal to K into S minus Z1, S minus Z2 to S minus Zm, and upon S minus P1, S minus P2, S minus Pn. What it means? There are M zeros and N poles in the GSHS. GSHS is what? This is the open loop transfer function of the system. Okay. So the characteristic equation of this system will be QS is equal to 1 plus GSHS, right? You remember this? QS is the characteristic equation, okay? And characteristic equation QS is equal to 1 plus GSHS. To represent this in the same format, if you multiply, or you, what we say, equate the denominators, here you will get multiply by this term to 1 and plus k into this term, and we again factorize. So these factors will change, the numerator factors. Okay. However, the number of the factors will be the same, and the denominator will remain the same, right? Now this is very important to note. This is representation of QS. QS is equal to 1 minus Z1 dash or Z1 bar. Why I have said Z1 bar? Because this Z1 and this Z1 bar are different. Because here P1 is multiplied, 1 is multiplied by this, then the K is multiplied here, and the addition has taken place, and then we have factorized. Okay. So these numerator factors here and here are different. Now comes the tricky part about the words. Okay. What are the closed loop poles? What are the closed loop poles of the system? Remember, this is the open loop system, right? So P1, P2, Pn, these are OLTF. What are these? OLTF poles, right? What are the OLTF what are the CLTF poles now? Closed loop poles. The closed loop poles are these ones. Am I right? How do you define a closed loop pole? A closed loop pole is the root of the characteristic equation. Means what is the root of the characteristic equation? Characteristic equation के roots म्हणजे काय? The roots of the characteristic equation means the value of S which will make the characteristic equation equal to 0. How will this QS become 0? QS will become 0 if S is equal to Z1 dash or Z2 dash or Zm dash. Means the zeros of QS are the poles of closed loop transfer function. Okay, you getting this point? The zeros of QS are the
Yes.
roots of the characteristic equation, and they are the same as the zeros of QS are the roots of the characteristic equation, means they are the CLTF poles. Am I right? Do you get this concept? What I have said?
Yes.
Okay, we are talking about the basic things. Zeros means what? Whenever an equation becomes 0, that value is called a 0. So roots of characteristic equation is the zeros of the characteristic equation, and that means those are the poles of the closed loop transfer function or the closed loop poles of the system. And for stability, what we want, all the roots of the characteristic equation should be on the left half of the S plane. This is the condition for stability as usual. Means all the zeros of QS must be on the left hand side. Means what? All these, this section on the numerator, this Zm, Z2 dash, Z1 dash, all of these should be on the left hand side. Okay. Now again take a look at this equation QS. This P1, P2, Pn, these are the poles of QS, right? These are also poles of GSHS, right? P1, P2, Pn, all these are poles of GSHS. So if some of these lie on the right hand side, what will happen? If Pn, P2, P1, any one of these are on the right hand side, this GSHS will be unstable, right? That is clear. If open loop poles are in the right hand side, the open loop system is unstable. Okay, but this is a very big ifs and buts. Okay, even if the open loop system is unstable, it is possible that all these Z1 dash, Z2 dash, Zm dash may lie on the left hand side. So even if the open loop transfer function is unstable, the system, closed loop system, still can be or may be stable. Okay. Therefore, there will be two cases that we'll have to analyze. There can be a possibility that the open loop system is stable. What about the closed loop system stability? There can be a possibility that open loop system is unstable, and what about the closed loop system stability? Okay, so for this closed loop system stability, we need to investigate if there are any roots of QS in the RHS, obviously. Okay, now to investigate this, we need to check whether any of the zeros of QS, zeros of QS means poles of the closed loop system, if any of those lie on the right hand side. That is what is required on the for the stability. Okay, so for this what we do is we choose a contour that completely encloses the right half of the S plane. Okay, now this is the S plane, this complete thing is the S plane. Okay, and this is the whole, and what we are saying is we are creating a contour. Okay, and what this contour is doing is there is a line segment C1. Okay, this C1, this line segment C1 is having infinite length. You can see it is starting from minus infinity and going towards plus infinity. Okay, it is along the imaginary axis. And we have uh, another line segment which is C2. It is r e raised to j infinity. Okay, and this r is tending towards infinity. Means what will happen? This whole of the right hand side of this S plane will be covered through this contour. Means this contour is starting from positive infinity, going towards full infinity, and coming towards minus infinity. Right? This is how the this contour is, and this contour is called Nyquist contour. Okay. Okay. This is called the Nyquist contour. So, uh, as I said, this contour is enclosing the complete right hand side of the S plane. Okay. Now what we are trying to investigate is if this contour encloses any of the right half of S plane poles and zeros of QS. This QS is there, 1 plus GSHS. Okay. So we are going to see whether any of the poles and zeros of this contour are enclosed by of this QS are enclosed by this contour. Okay. So suppose there are Z zeros, okay, and P poles of QS in the right half of S plane. Okay. So if as the S moves along the Nyquist contour in S plane, a closed contour is traversed in the QS plane which encloses the origin N is equal to P minus Z times in the counterclockwise direction. Now, why is it so? Why is it so? Because if you remember in the at the time of discussion of the closed contour thing, okay, the for enclosing poles and enclosing zeros, there will be angles 2 pi and minus 2 pi for each pole and each zero, right? So overall, the origin will be enclosed P minus Z times. Enclosed means the total angle will be N multiplied by 2 pi. Okay, P is the number of poles, Z is the number of zeros, which are on the right half of S plane. Okay, so what it means, if a system is stable, there should be no zero of QS in the right half of S plane, means Z should be equal to 0, means Z should be equal to P. Here, from here, Z should be equal to P, means there should not be any encirclement of the origin. Okay, there should not be any encirclement of the origin in this case. Okay, so what it means is, for a closed loop system to be stable, the number of counterclockwise encirclement of origin should be equal to the number of right half of S plane poles. Counterclockwise encirclement, okay, right, means the minus 2 pi 2 pi angles multiplied by that many poles. Okay, that should be equal to the number of right half of S plane poles. And open loop poles, these open loop poles means the unstable poles of the transfer function of GSHS. Okay, what we are talking about, if there are any S plane poles of QS, means if there are any unstable poles of open loop transfer function. Okay, for that case, the number of encirclements, clockwise encirclements of origin should be equal to that many poles. But if the open loop system is stable, means there is nothing on the right hand side, then the number of encirclement should be equal to 0. Okay, so these are the two basic important things to remember. If there are any open loop poles on the right hand side, then the origin should be encircled in the counterclockwise direction n number of times, where n will be equal to the number of right hand side poles. and if there are no right hand side poles, then there should not be any encirclement of the origin. Okay. Now encirclement of origin means what? If just take a look at this, GSHS is equal to 1 plus GSHS minus 1, right? Okay. So what we are having, counter the contour of GSHS we are talking about, right? Origin encirclement in case of GSHS contour. So it will be the same as 1 plus GSHS drawn from the minus 1 plus 0. Like here, okay. This is 1 plus GSHS contour, and if I take 1 plus GHS minus 1 means only GS, then that encirclement will be of the point minus 1 J0. Are you getting this concept? See, this is 1 plus GSHS contour and this is the origin. But if I subtract from this whole function minus 1, what I get? I get only GS. So this contour will get shifted to here. This will become the new origin for this contour. And encirclement should be considered for now this point, minus 1, J0. So now coming back to our final conclusion from this lecture, that there will be two situations as we have been talking about. The open loop system is unstable. Okay. Means what? The open loop system has some poles which are on the right hand side of the S-plane. So in this case, the contour should encircle the point minus 1 plus J0 in counterclockwise direction as many times as the number of right half of S-planes. Okay. So if there are, let's say, two poles of GSHS on the right hand side, then the contour should encircle this point twice. There should be 2 times the encirclement of this point. And if the system is open loop stable, means what? There is no pole of the open loop system in the right hand side plane, then in that case, this point should not be encircled. Okay, the GH should not encircle this point. Okay, so now it is very difficult to solve a problem actually through this way. But what you can do now, you can go in the you can see our notes. There are some solved problems in that. Okay, for that for there you can see uh, how that problem is solved. Basically, uh, we will need to, of course, we need to define the Nyquist contour, and uh, whatever we have seen in the polar plot, how to draw the polar plot. Actually, that sections we are going to need in the while drawing the Nyquist plot. Okay, so uh, these are the two things to remember very importantly. How to draw the Nyquist plot is very similar to drawing the polar plots. Just go through that example. But once you draw the Nyquist plot, talking about stability is important. While talking about stability or while defining the stability, these two things are very important to know. Okay, if the system is open loop unstable, how will you find out this? Just look at the open loop transfer function, means the whatever transfer function is given GSHS. If there are any poles which are on the right hand side, means the open loop system is unstable. In that case, if there are two poles, then encirclement should be twice. If there are one pole, that encirclement should be once. And if there are no poles on the right hand side, means the open loop system is stable, then the point minus 1 J0 should not be encircled by the Nyquist plot. Okay, so this is how you will have to tackle this problem of Nyquist stability. Okay, I will try to do something for to demonstrate the how to solve this problem. Okay, it is not possible for me to draw these things right on this in this way, but I will try to do something else. Okay, do you have any questions regarding this Nyquist stability criterion right now? Are you getting what we
No.
have discussed? How this stability is coming up to? I'm just going back to what we have seen. Okay. Stability, whenever we are talking about stability, we must know we are talking about, always we are talking about roots of the characteristic equation. Characteristic equation is 1 plus GHSS equal to 0. Roots of this equation means zeros of that equation. Means the numerator things. And the denominators are the same poles of the open loop transfer function. Okay. So we should you should just keep these things in mind what we are talking about. Okay. Zeros of characteristic equation are the poles of the closed loop transfer function. Okay. Uh, Anybody having questions?
No. No,
No
sir.
one? Are you getting what we have
Yes,
discussed?
sir.
Yeah.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. Who said yes? I think Mohit, Shivanjali, or someone else.
Yes.
Yeah.
Yes,
See,
sir.
I know this point is a little bit difficult to understand. Okay. Okay. Uh, yeah. So if you have any questions, you can ask me, or you later also we can we can discuss on our group. Okay. Yeah. So shall we stop here?
Yes, sir.
Yeah.
Yes, sir.
Okay. So
Yes, sir.
yes.
Yes,
Thank
sir.
you. Thank you, sir.
You are always welcome. No problem.
Thank you, sir.
Yeah.
Thank you, sir.
So I will stop here now. If you get any, I will suggest you go through the notes as well as some solved examples from other books, and try to practice whatever is given. Okay. Don't think these are difficult things. They are very simple things actually. Okay. Just remember the basics. Whatever we have seen in the today's PPT, I have already shared with this that PPT with you already. Whatever the whatever is written about stability, like roots, then poles and zeros, OLTF, closed loop poles, open loop poles, those things you just make yourself clear with. Okay, because that is very important for you to clarify whatever you are saying. Closed loop pole, open loop pole, closed loop zero, open loop zero, and then poles of the QS and zeros of QS. All these things are now getting, you may find they are getting a little bit confused. So just try to think, practice it, and also practice the problems. Okay, because without practice it will be very difficult for you to go through all these things. Okay.
Okay, sir.
Or I will try to upload this video also on YouTube if it is possible. Okay, so that you can afterwards also you can go through it. Okay.
Yes,
PPT
sir.
are already shared with you, and the notes are already available on Moodle. Okay, I will soon upload.
Sir, one doubt.
Yeah.
Sir, one doubt.
Yeah.
सर सेमिलॉग पेपरवरच काढायचं का?
नाही नाही, हा जो नायक्विस्ट आणि बोर्डे सॉरी नायक्विस्ट आणि पोलर प्लॉट हे सिंपल ग्राफ पेपरवर आहे.
सिंपल ग्राफ पेपर.
हो हो. Because you can see there is only real and imaginary part in that. Only Bode plot we need semilog paper, because for that we need a long frequency range. Here we are not having frequency as a variable. If you remember, there is no frequency variable on the graph, right?
Yes, sir.
It's only real and
Yes.
imaginary part.
Yes.
That those are not those don't go out of range. Okay.
Okay, sir.
Okay, these are on simple graph paper. Even yeah. Okay. Anything else? Okay, so we'll stop here. You you must practice. That is very important. Okay, and the situation may extend the lockdown. This is my guess. So you must study home. Try to cover as much as possible things. Go through reference books also. Okay, and if you have doubts, put those on our T electrical group. We will try to discuss over that. And if there are many things which are common to all, we will arrange some other lecture also. Okay.
Okay,
Okay,
sir.
sir. Thank
Yeah.
you.
So
Okay, thank you.
take care. Stay home. No one is going out, right?
Yes, sir. No one is
Yes.
going out.
Yes.
Yeah. Because if you go out, you may not feel anything, but you may infect your uh, people in your home, right? You have read वाचलंय ना सगळं त्याच्याबद्दल.
वाचलंय की सर.
हा,
Oh,
म्हणजे
sir.
तुम्हाला काही होणार नाही. यू आर यंग पीपल. You have good immunity power. So you may become just passive carriers. Okay. It is not only
Yes,
for
sir.
you to remain safe at home. It is also for your parents, your uh, other people at your
Family.
home. Okay. So take care
Yes.
of that also. Okay. घराच्या बाहेर पडायची आणि काही आवश्यकता नाही आहे कशाचं काही. घरात थांबा, व्यवस्थित अभ्यास करा. ओके.
हो,
Yes,
सर.
sir.
Yes, sir.
काहीतरी
Okay.
दुसरंही वाचा.
Thank you.
म्हणजे फक्त अभ्यासच करत बसायचं असं नाही. काहीतरी चांगला गोष्ट वाचा, चांगली साहित्य वाचा वाटल्यास. टू टेक अ ब्रेक. Okay, because my guess is it may going to take a longer time for this lockdown to get up. The situation may become worse, so keep yourself healthy, mentally strong. Okay.
Yes.
Yes.
Okay, so all the best. Okay, if you have any
Thank you,
doubts,
sir.
put them on our T electrical group also. Okay, so bye.
Okay, sir.
Bye bye.
Thank
Bye,
you, sir.
sir. Thank you, sir.
Thank you, sir. Bye.
Thank you, sir.